The U.S. Army Corps of Engineers, or USACE, has set an ambitious goal to beneficially use 70% of its dredged sediment by 2030. It's a big challenge that will require innovative solutions for fine-grained dredged sediments that cannot be used for beneficial use applications, such as beach nourishment. Researchers at the U.S. Army Engineer Research and Development Center, or ERDC, Environmental Laboratory, are working to overcome these challenges as they develop methods for deploying dredged sediment as feeder stock in 3D printing.
What makes what we're doing important is because we're reframing how dredged material can be used. We're reframing in a way that is beneficial use, the public perception of how dredged material is being used in a way that is cost effective. And so we're trying to tie all those things in to make it where at the end of the day, it's looked at as something that is a good thing and not necessarily something that's bad and waste, but it's something that we can use every day in what we're trying to achieve.
Beyond the mechanical processes of using dredged sediment for 3D printing, ERDC researchers are also pioneering pre- and post-processing methods that will help determine the material's feasibility for being reintroduced into the environment as printed objects. Little data on this process currently exists, and ERDC researchers are looking to close that knowledge gap.
Some of the challenges of getting out dredged sediment into the environment through additive manufacturing really deal with what type of sediment it is, where it's sandy or silty, and you have to have some type of pre- or post-processing to help the durability, depending on what you're trying to do with it. There is also that potential that a contaminant might leach out of the sediment, and so here at ERDC, we're really working on trying to understand the potential for that. And then if it does leach out, we're trying to put in more natural additives, such as a zeolite that can sequester that contaminant before it even leaches out into the environment.
So the pre and post processing consists of numerous steps, but for the more important steps of that pre and processing, it just mainly consists of drying, grinding, and sieving, and the post processing of actually printing the structures and allowing them to air dry and then placing a kiln for up to 12 hours. Once the structures are removed from the kiln, that's when we start the latter part of our post-processing. And that process consists of where we're tumbling the prints for over 4 days. The purpose of the rotating is to mimic environmental conditions. And so we take the solution from those prints and we spin them down and we do an acute toxicity test. So based on the sediment that's used, depends on the solution that we're using, if it's fresh water or marine. And so that determines the species that we also use. And from that tells us if there is any leaching from the structures that we printed, that it has dredged material incorporated into it. And so if we do see toxicity, or if we don't, this tells us that what we're currently doing in the tests and the prints that we have, there's no leaching. And so when we use it out in the environment, those prints on a larger scale go out, what we've done has been successful.
The next phase of this project will also be game-changing for optimizing the use of dredged sediment.
And being able to have it from a lab setting to on-site setting where we're able to possibly print on-site or print on a larger scale to see that beneficial use of what we're currently doing.